Warning, the solar system is inside a protected dead zone. Get this, our entire solar system sits inside a dead zone in space. Signals bend, dust thins, stars look wrong right around us. If that's true, contact is muffled, data is biased, and our growth hits a ceiling we can't see. So who built the bubble and why keep us inside? I'm telling you, star maps don't add up, light looks clean, and there's a signal leak we were not meant to catch. We're running a 3-act investigation, hard data first, then the unsettling function. Hold on, because the walls around us show structure they shouldn't, and they act like filters. The world inside the bubble. Here's the thing. Astronomers agree we live inside a low-density cavity called the local bubble. It isn't small. Think several hundred light-years across, roughly 1,000 light-years end to end in its longest direction, shaped like a lumpy peanut. The leading natural story says it formed over the last 10 to 15 million years from a chain of nearby supernovae. We didn't watch that happen. We infer it from dust extinction, neutral hydrogen, and the way nearby molecular clouds draw a ragged ring around us. Our sun isn't centered. It rides near the bubble's edge, touching the local interstellar cloud, a warm, partly ionized patch that wraps us like gauze. That edge matters because it's where our neighborhood couples to the rest of the galaxy. Dust, gas, magnetic fields, and cosmic rays all meet there, and that interface talks back. Around the rim sit famous clouds, Taurus, Perseus, Ophiuchus, like bright knots stitched into a shell. Now, if this were just leftover debris, you'd expect a messy fade from dense to diffuse. But the data keep throwing sharp features. 3-dimensional dust tomography, built from millions of stellar colors, brightness shifts, and Gaia distances, shows pronounced shells and filaments instead of a smooth cavity. Polarized starlight traces magnetic fields that seem to run along those structures. You get arcs of neutral hydrogen that line up across hundreds of light years, like ribs. It's not a clean sphere, but the edges are weirdly crisp in places. Different instruments cut through different layers. Gaia nails parallax distances and proper motions, giving us a 3D skeleton. Hubble and other UV spectrographs read absorption lines like CII, CII, and OVI along sightlines to nearby stars, sketching temperature and ionization of the gas we sit in. Soft X-ray backgrounds flag hotter plasma in and around the cavity. Even radio surveys map electrons through dispersion and Faraday rotation. Stitch them together, and the cavity pops out in relief. So what's the central question? Is this just a superbubble carved by clustered supernovae, messy, natural, decaying? Or are we living inside a hardware-level isolation zone that acts on light and particles like a system design? Most of astronomy leans natural, obviously. But the stakes for us are real if it functions as a filter. If the bubble cleans signals, we could be overestimating nearby stellar luminosities when dust is undercounted locally. If it scrambles polarization, we might be misreading magnetic coherence. If it sets an electron floor, radio pulses could look closer than they are. Even habitability estimates change if cosmic rays and dust delivery were modulated by this cavity for millions of years. We also have timing clues that tie Earth to the sky. Deep sea crusts and sediments carry live iron, a radionuclide made in supernovae, with peaks around 1.7 to 3.2 million years ago and 6.5 to 8.7 million years ago. That's the smoking gun for nearby blasts sweeping past. Simulations link those explosions to the same moving groups thought to have carved the local bubble, matching the 10 to 15 million year window. The timeline says we rode shock fronts more than once. And then there's a boundary you can feel. As Voyager 2 crossed the heliopause, it measured a step change. Temperature and density jumps that looked like slamming into a roughly 50,000 degree plasma skin. Not a brick wall, but a defined layer. That wall of fire isn't the local bubble shell itself. It's the boundary of our heliosphere pressing into the local medium. But it proves interfaces out here can be sharp and structured. It also shows how solar wind pressure, interstellar pressure, and magnetic fields set up real filters. Zoom out and our whole neighborhood moves. The Milky Way within the Laniakea supercluster drifts roughly 600 kilometers per second toward the region called the Great Attractor. That's normal large-scale flow, sure, but it's a reminder. Reference frames leak. Gravity, motion, and background structure seep into every measurement. If there's a reality leak, it's that nothing we see is free of the medium it crossed to reach us. Back to local oddities. Dust scarcity near us makes stars look bluer and cleaner than the galactic average. So if you naively correct for reddening, you can misjudge distances and ages. Stellar scintillation and polarization differ inside the cavity compared to just beyond it. Even dispersion measures along very local pulsar sightlines sit on a baseline, an electron floor, consistent with a cavity interior filled with warm ionized gas. None of this proves design. But stack these features, and you get a bubble that behaves more like a device than a scar. So here's the lock-in. We accept the local bubble exists. We accept a supernova chain probably made it. But the walls show structure they shouldn't, the interfaces act like filters, and our instruments see sharpness where turbulence should smear. If it's just nature, great, we can model it. If it's maintenance, we have a different kind of problem. Next, we push on the edges. What are these walls made of, and why do they hold their shape? The walls that shouldn't be there. So let's walk straight into the wall. Three-dimensional dust maps from Gaia-anchored tomography don't show a gentle fade. They show edges, sharp corrugated shells. Filaments bite into space instead of blending out. If this cavity were just a tired superbubble coasting toward equilibrium, turbulence should smear the boundary into fuzz. But in multiple independent reconstructions, dust density ramps up over only tens of light years into seams you can trace around the sky. Not a perfect ring, more like a cracked eggshell, with panels that in places look machine-cut. Now layer radio on top. Neutral hydrogen, Hi, lights up in long arcs that keep the same curvature over hundreds of light years. You get sweeping ridges that act like ribs holding shape against pressure. That's tough to get if each patch was battered randomly by shocks at different times. Polarized starlight backs it up. Grains on those walls align with magnetic fields that run along the structure, not across it. The vectors twist in concert, as if the field is draped over a frame. Nature can drape, sure. But the coherence here is neat, tidy in places that should be messy. Look where the rim is alive. Taurus, Perseus, Ophiuchus. They perch right on the shell, dense and busy with new stars. That fits the textbook. Shocks compress gas, gas forms stars. But thickness and spacing across sectors keep clustering into similar column densities and repeating widths. Not identical, but tighter than a free-for-all. Some lines of sight even show double shells, nested layers like a laminate. Single blasts don't love that outcome. You need repeated stress, periodic pressurizing, or reinforcement to stack layers that cleanly. Temperature tells the same story. Ultraviolet absorption toward nearby hot stars, CII, OVI, shows a staircase of ionization and temperature moving from inside to edge. Warm, partly ionized gas inside, a hotter, thinner skin, then cold, dense molecular walls. A gradient, yes, but stepped, not smooth. Soft X-ray maps add a glow that hugs the interior, a halo that looks like a hot plasma skin skimming the cavity's inner face. Picture drywall, insulation, brick, layers that do different jobs, stacked with intent by the physics. And then there's alignment across methods. Dust tomography says shell here. Hi arcs say curve here. Polarization vectors ride the same curve. Star formation sits right on top. That cross-check is what tightens the noose. Any single dataset can mislead. All of them pointing to the same seams is either a triumph of multi-messenger mapping or a coincidence spree we shouldn't wave away. But wait, what carves and keeps those seams so crisp? The natural model says stacked supernovae from moving groups over the last 10 to 15 million years carved overlapping cavities that merged into a superbubble. Colliding shells make filaments. Magnetic fields shape ragged edges. Cooling builds skins. Simulations do produce sharp bits. The problem is persistence. These edges have stayed sharp while our sun surfed near them for millions of years. Shear, diffusion, and magnetic reconnection should chew on that outline, yet some parts look maintained. Velocity data says the wall isn't just there, it's guiding traffic. HI often carries flow signatures that point to gas sliding along the shell, like cars in a roundabout. Azimuthal motion dominates over punch-through. That's containment. Add magnetic tension, and you get rails that discourage cross-boundary mixing. It's a natural Faraday-like geometry, barriers that separate thermal, magnetic, and kinetic modes by layer, channeling motion tangentially. We also see filaments bridging segments, narrow, surprisingly straight. Rotate those into 3D, and a few line up with known magnetic domains in the local interstellar medium. They act like braces, tension members stitching panels together. Think truss, not soap film. I'm not saying scaffolding, I'm saying field. Gas coupling is doing structural work that looks designed because it's efficient. Here's where sharpness matters. In physics, sharp transitions flag thresholds, phase changes, instabilities, chemistry, and cooling flips that divide regimes. Across the bubble wall, we tick several: cooling curves that favor sudden condensation, ionization balances that flip at modest column depths, magnetic pressures that jump once dust and gas couple tightly. Stack enough thresholds and the interface behaves like a switch. You push continuous input, you get discrete output. That's how devices work. Therefore, the wall isn't just a boundary you can draw, it's a filter bank. It sorts by particle charge and energy. It delays low-frequency radio more than high. It rotates polarization one way on approach, twists it again on exit. It seeds star formation where pressure waves pile up and quenches it where tension holds. So when we look outward from inside, we are not seeing through space. We are seeing across a device-like interface that edits the signal. You want a sanity check? The heliopause proves interfaces bite. Voyager 2 hit a roughly 50,000 degree plasma skin at the sun's boundary, a narrow, structured layer with sharp jumps in density and magnetic angle. That's a smaller inner example of the same physics. Layered plasma, ordered fields, sudden transitions. Scale that up, give it millions of years of shaping, and the local bubble's crisp seems stopped looking like an accident. So if the wall behaves like a filter, the next question writes itself. What is it doing to light and particles exactly, and how do we catch it in the act without fooling ourselves? The Faraday cage hypothesis. So let's test the bolder idea. The local bubble doesn't just sit there. It behaves like a Faraday cage on galactic scales. Not a perfect shield, but a layered system that shapes how charged particles and electromagnetic noise move, clean up, and reach us. If that's true, signals inside look brighter, cleaner, maybe even closer than they are. And contact, it could be muffled before it ever starts. Start with the sun's bubble inside the bubble. The heliosphere is our personal plasma envelope, inflated by the solar wind and pressed by the local interstellar cloud. Where they meet, Voyager 2 crossed a narrow interface and felt a jolt, sharp jumps in density, magnetic angle, and a roughly 50,000 degree plasma skin. That is measure, not myth. The point isn't that the heliopause is the local bubble wall. It's proof that space builds real, layered boundaries with electromagnetic teeth. Those layers reflect, absorb, refract, and reroute charge. Now zoom out. The local bubble's interior isn't empty. It holds warm, ionized gas that sets an electron floor. Low-frequency radio picks up extra dispersion even over short local paths. Pulsar and fast radio burst observers account for this, but if you undercount local electrons, sources look a touch closer and cleaner than they are. Dust scarcity doubles that bias by making stars bluer. A cage doesn't have to block to mislead. It just has to bias what gets through. Magnetic fields do the steering. Galactic fields are rails and charged particles spiral along them. Where the bubble wall compresses gas, it amplifies and orders the field. Ordered fields raise the odds that particles mirror, scatter, and diffuse along the shell instead of punching through. Pitch angle scattering, magnetic mirroring, turbulent diffusion, textbook transport. Put it on a coherent curved shell, and geometry starts to look like intention. Particles skim. They leak at seams. They pile at corners. We see the consequences across timescales. Cosmogenic isotopes, beryllium-10 and carbon-14, record long, smooth swings in Earth archives when cosmic rays shift. Live iron-60 in deep-sea crusts, with peaks near 1.7 to 3.2 million years ago and 6.5 to 8.7 million years ago, ties those shifts to nearby supernovae. A raw blast should spike and fade. The record shows shoulders and plateaus, like the flux slid along a boundary before leaking in. That smoothing reads like filtering by a structured cavity. Soft X-rays backstop the layering. A thin hot skin near interfaces scatters and absorbs soft X-rays that would otherwise haze the sky. For years, the soft X-ray background confused people, local or distant. The answer is both. But there's a local globe that hugs boundaries and even casts shadows against nearby clouds, like Taurus and Ophiuchus. That's backlighting from our side, a signature of stacked layers editing photons by energy band. Okay, but can a lumpy superbubble act like a Faraday cage in radio terms? Not with metal walls, but with gradients in electron density and magnetic strength that change slowly inside, then jump at the rim. In plasma, a gradient plus a discontinuity is a filter. Group velocities change. Polarization rotates. Low-frequency modes see a different refractive index than high. Suddenly, inside observers measure coherent polarization twists that track the shell and mistake that coherence for a property of distant sources. Dust grains aligned by fields polarized starlight. Magnetized plasma rotates radio polarization. A layered interface can align both. Tidy, but local. There's dynamics too. The heliosphere breathes with the solar cycle. The sun drifts through denser and thinner strands of the local interstellar cloud. Coupling changes. Galactic cosmic ray flux at Earth swings in ways heliospheric models alone struggle to explain in some epochs. Ground-level muon counts respond. Spacecraft see spectral kinks. These aren't smoking guns, but they look like a double gate system in action. Heliosphere as inner gate, warm ionized corridor in between, bubble wall as outer gate. Gates shape what gets in, what mirrors, what resonates. But wait, light isn't the only messenger. If curation is real, high-energy particles should still slip, and when they do, the pattern should point at geometry. TV energy anisotropies on the sky show faint excesses and deficits. One broad excess hugs rim directions where adjacent superbubbles crowd the wall. You can call it a nearby source. Or you can tilt a magnetic mirror on a curved shell and beam certain pitch angles back, reflection from a seam. Here's the thing that tightens the case. When you rotate starlight polarization by subtracting a model of shell-driven Faraday rotation, residuals shrink more than they should if turbulence ruled. That means a big chunk of what we think is interstellar polarization lives in the interface we're looking through. Add dispersion baselines from very local pulsars, proof of an electron floor, and the slope breaks near the suspected rim, steepening early in some directions, flattening in others. Structured sheets inside the cavity would do exactly that. So the Faraday cage hypothesis, as a working model, says this. The local bubble is a multi-layer filter bank. It scrubs soft X-rays with thin hot skins, rotates and polarizes light through aligned grains and magnetized plasma, sets an electron floor that biases radio dispersion, and confines or redirects charged particles along ordered fields at the shell. None of that requires intent, but function matters more than motive. A device is defined by what it does. Therefore, don't argue from vibes, test the curation. Map where polarization twists track curvature. Pin the electron floor with nearby pulsars and FRBs that skim the rim. Watch soft X-ray shadows for changes. If the layers are editing, those edits will line up across bands and shift together when the interface breathes. And if they do, the next move is obvious. Catch the editor in the act. Rising tension, star maps that don't agree. So let's put the filter idea under pressure with the maps that hate to be wrong. Start with Gaia. Parallax is geometry. You don't argue with triangles. A star's tiny wobble says 120 parsecs, period. Now look along the same sightline with dust reddening. Inside the local bubble, dust is scarce, so colors should barely change until you smack the shell. But get this, in multiple rim directions, reddening ramps up tens of parsecs before Gaia says you've reached dense material. The dust map whispers edge early. Gaia says not yet. That early veil is thin but systematic. It's an extra layer cutting in front of the true wall. Flip bands. Ultraviolet absorption lines toward nearby hot stars trace the warm, partly ionized gas along the path. Ions like CII, OI in several of those early veil sightlines. UV says you're already in warmer, more ionized material sooner than the dust expects. So dust says edge late, UV says gas edge early, and Gaia pins the stars where geometry puts them. Each is honest about its layer. Together they don't land the same boundary. Standard candles make the mismatch expensive. Take a young cluster perched near a shell segment. If you assume a typical local dust-to-gas ratio, you correct its brightness and get a distance a hair too small compared to Gaia. Why? Because the foreground dust is weirdly thin and patchy inside the cavity, so your correction overshoots. Here's the kicker. That bias repeats around the sky in sectors that hug the bubble's outline. One region is a mistake. A ring of them is a system. Polarization piles on. Starlight polarization vectors should wander if turbulence runs the show. Instead, they swing smoothly along arcs that trace the shell, then twist again where arcs intersect. You can literally read curvature off the angles, like contour lines on a map. When teams derotate those vectors by subtracting a model of Faraday rotation attributable to the shell, the residual scatter shrinks more than expected. Translation. A chunk of what we called interstellar polarization is the interface we're looking through, not the distant sources. Radio nails the baseline. Dispersion measures to very local pulsars, tens to a few hundred parsecs, stack on a floor you can't wish away. There's an electron minimum in the cavity. Plot dm versus Gaia distance and you expect a tidy ramp. Instead, the slope breaks near the suspected shell, steeper ahead of schedule here, flatter there. That's what you get if thin sheets of electrons live inside the cavity, widening and narrowing the corridor toward the wall. It's a floor with furniture. Here's a clean corridor test. Pick a line of sight that grazed the torus edge. Gaia fixes distances to foreground stars. Reddening rises slower than you predict, so those stars look slightly bluer and brighter. Polarization vectors rotate steadily as you sweep the rim, tracking the shell's arc. UV absorption shows a warm skin sliding along the wall at a velocity offset from the cold molecular gas. A pulsar just behind the region shows a dm jump right at the turn. Every modality says layered interface here, but none puts the true wall at the same depth. That's not noise, that's a stack of filters. Okay, but if everything is messy, why do independent methods still agree there's a bubble? Because the first-order picture holds. Gaia's 3D skeleton, dust tomography, UV absorption, soft X-rays, radiopolarization, they all outline the same giant cavity and dense rim. The fight lives in the second-order details, where each layer starts, how steeply it rises, how fields twist light. Those are exactly the details that matter if the wall edits signals. Now, why should you care beyond map drama? Because calibrations live here. Distance ladders anchor on nearby clusters. Extinction laws are tuned locally. Magnetic field reconstructions lean on polarization priors. If our neighborhood preprocesses light and charge, then the local standard bakes in bias. Export that bias to the wider galaxy, and you carry the error into star formation histories, mass-to-light ratios, even exoplanet radii. That's a slow burn problem. Your ruler's first inch is wrong. We can't hand-wave it away with turbulence is complicated. Look at the pattern of disagreement. The early dust ramp clusters along the rim. Polarization angles align to the same curvature. dm slope breaks near the same sectors. UV skins slide along the same surfaces. These features correlate with geometry, not chance. So the paradox hardens. The cavity is real. The shell is real. The big shape is solid. But the layers refuse to agree on the exact edge, depth, thickness, twist strength, all the things that define a filter. Either nature stacked thresholds into a device-like interface by accident, or we live behind a system that selects what we see. Light can be curated. Particles are harder to fake. If the wall edits photons, do high-energy messengers still slip? And if they do they point back at the same seams? That's where we go next. The cosmic ray puzzle. Particles don't care about pretty maps. They punch in, leave scars, and keep bad secrets. So if the wall is curating light, cosmic rays should carry the edit marks. Start with the slow clock we can hold in our hands, cosmogenic isotopes. Earth's archives, ice, tree rings, deep-sea crusts, show long, smooth swings in beryllium-10 and carbon-14 when the high-energy range shifts. Layered on top is the clincher. Live iron-60 in seafloor crusts, peaking about 1.7 to 3.2 million years ago and again 6.5 to 8.7 million years ago. You don't make iron-60 on Earth. You get it from nearby supernovae. A single raw blast should spike sharp, then fade. But the isotopes don't look like needles. They look like shoulders and plateaus, as if the flux hit a boundary, slid along it, then leaked in at seams. That's what a structured cavity does. Magnetic mirroring and turbulence scatter particles azimuthally. Only certain pitch angles thread to the inner system. The wall smooths time, not because it's kind, but because transport prefers the shell. We saw the handoff up close. When Voyager 1 and Voyager 2 reached the heliopause, they watched galactic cosmic rays rise as the sun's magnetic cocoon ended. If the heliopause were the only gate, you'd expect one clean step. Instead, both spacecraft recorded layered gradients and anisotropies, plus a sharp rotation in field angle. Voyager 2 also measured a narrow, roughly 50,000-degree plasma skin. Inside that skin, low-energy particles stayed suppressed. Just outside, they jumped, not identically at both probes and not all at once. That screams two-gate control. Heliosphere inside, local interstellar medium outside, with the wall's ordered fields shaping what finally gets in. Zoom to higher energies. Detectors in orbit like M02 see an excess of positrons at tens to hundreds of GeV. People argue sources, pulsars, dark matter, but geometry matters too. If primaries bounce and dwell in the bubble's rim, they collide more in the dense shell. Those interactions make secondaries, positrons included, that can leak back along ordered fields. From a vantage near the edge, that confinement can tilt the ratio we measure without demanding exotic physics. I'm not saying the bubble explains the whole positron bump. I'm saying a maintained rim can bias spectra right where local transport distances matter. On the ground, muon networks catch the weather of this particle climate. Day to day, the sun rules. But during certain epochs, counts at multiple stations swing together in ways that don't track heliospheric models alone. When local field geometry opens corridors toward the galactic plane, or when the sun noses into denser strands of the local interstellar cloud, coupling changes. A double-gate system fits. Inner gate breathes with the solar cycle. Outer gate shifts with the wall's state. Small signals, consistent direction. Anisotropy ties it to the shell. At TV energies, where gyroradii are big and bending is harder, sky maps still show broad excesses and deficits at parts per thousand levels. One prominent excess hugs directions, where the local bubble's rim crowds against neighboring superbubbles. Call it a nearby emitter if you want. But a curved magnetic mirror on a coherent shell will beam certain pitch angles back toward us, making a bright seam that drifts with energy. The hotspot shifts with energy like transport, not like a single fixed lighthouse. Now test the sieve logic against time profiles. Those iron-60 peaks line up with the same 10 to 15 million year supernova chain that carved the cavity. Hydrodynamic simulations that track ejecta mixing into a warm, magnetized medium reproduce both the timing and intensity if the surrounding density is low, and the supershell reflects some waves. Reflection at a shell is the key word. It means the wall can send a shock back through the interior, extend delivery windows, and stretch isotope signals into the plateaus we actually see. This is where stakes get practical. If the bubble edits cosmic rays, then our baseline galactic spectrum isn't purely galactic, it's locally reprocessed. That bleeds into dark matter searches, pulsar halo modeling, even radiation risk for interplanetary flight. Worse, time-variable outer gate behavior means long records, ice cores, crusts, our convolving source and filter. Untangling them needs phase. When did corridors open? When did they pinch? And how did the electron floor inside the cavity set low energy cutoffs? So how do we catch the filter in the act with particles? 3 moves. First, build a dense grid of rotation measures and dispersion along rim grazing lines. Then stack ground muon and neutron counts key to those corridors. If muon flux rises when polarization angles drift toward an open set point, that's a gate signature. Second, watch TV anisotropy hotspots with energy bend cadence and cross-correlate with soft X-ray brightening on the inner skin. If reflection efficiency changes when the skin heats, seams are doing the work. Third, fly cheap scouts to graze the rim. Each carries a compact cosmic ray stack and a multi-band transmitter. Measure spectra at the wall, ping back through it at angles we think are reflective, and see if inside receivers record the predicted gain bump. If the returns lock to geometry and phase, the verdict lands. We are not sipping the Milky Way raw. We're drinking what leaks through a layered sieve, heliosphere inside, warm ionized corridor compressed, ordered fields at the shell. Light lied politely. Particles told the same story in scuffs and bruises. And if both messengers point to the same seams, the next step is obvious. Find the leak in radio 2 and watch it flip in real time. The signal leak. Here, S where the wall slips. At TV energies, cosmic rays should fly nearly straight. Yet sky maps from ground arrays show a faint anisotropy, broad excesses and deficits at parts per thousand. One bright patch hugs directions where our rim crowds against neighboring superbubbles. You can say nearby source, sure, but tilt a magnetic mirror on a curved shell and you get beaming by pitch angle. A seam behaves like a reflector. The hotspot looks less like a lighthouse and more like a bright well. Now cross-check in photons. Soft X-ray maps show a glow that hugs the cavities inside, our thin hot skin. If that glow sits behind nearby clouds like Taurus or Ophiuchus, the clouds should cast crisp shadows. They do. That's backlighting from our side, not a distant haze. It's like shining a flashlight inside a tent. You see the poles as dark lines. Edges are lit, structured, and close. A living interface announces itself by throwing silhouettes. Radio should tell on it too. Fast radio bursts give you dispersion clocks and polarization twists, both sensitive to electrons and magnetic geometry. Along several rim grazing paths, FRBs arrive with dispersion measures a touch lower than the average Milky Way model predicts for that direction. If we undercounted local electrons globally, we'd see low DMs everywhere. We don't. The effect clusters near rim sectors, as if rays skim a corridor with fewer free electrons before slamming the dense wall. Think weak waveguide, a carved lane where certain modes slip farther with less delay. Polarization is the kicker. An FRB skimming one active panel came in with a rotation measure that flipped sign relative to the steady draped field model we built from years of starlight polarization and pulsar RMs. Same corridor, same field baseline, wrong sign, and it changed during the burst substructure. That's not a static sheet, that's a dial. Minutes later, all sky soft X-ray monitors logged a faint, brief brightening along the same sector. Coincidence? Maybe. But if a thin inner skin heated while field geometry reoriented, you'd get both. More electrons to twist polarization and a quick X-ray wink. Okay, test the leak without leaning on one weird day. We stack 3 tells across time and energy. 1. The TV hotspot shifts with energy the way a reflector's efficiency would, tight at one band, broader at another, while its centroid rides the shell's curvature. 2. Soft X-ray backlight throws stable shadows that sometimes brighten and fade in step with local polarization drifts, like the skin breathes. 3. FRBs that graze rim sectors show small, direction-dependent DM deficits paired with rotation measures that swing more than interior sightlines, and in a few cases, swing fast. Now, could turbulence fake this? Up to a point. Turbulence can rotate polarization. It can modulate X-rays by heating. It can bias CR arrival patterns. But turbulence loves random. What we see lines up with geometry. The anisotropy patch hugs a known seam. The X-ray flickers pop in the same panels where polarization drifts toward a set point, then snap back. The FRB with the wrong sign RM rode a corridor we already tagged as coherent from starlight, then briefly was. That's not chaos. That's a mode change on a structured boundary. Here's the practical therefore. If rim panels can flip state, open a little, close a little, then corridors aren't always the same. Some days radio gets less twisted and low-frequency modes leak more. Some days the skin heats, rotation spikes, and the gate pinches. And because the TV hotspot's gain depends on pitch angle, its shape with energy becomes a live readout of mirror efficiency. In plain terms, the wall broadcasts its mood if you watch the right meters. So we designed the catch in 3 layers. First, we put a phase chaser on the rim. Small arrays that watch starlight polarization and local rotation measures in real time along tagged panels. When angles drift toward open, we know. Second, we run reflection mapping. Synchronized beacon pings from deep space, grazing the shell at controlled angles and sweeping radio frequencies. If a panel behaves like a weak mirror, the return shows a gain bump and a phase lag fingerprint. Third, we tie particle weather to panel state. Ground muon networks and TV arrays time-bin their counts by the phase chasers, open-closed flags. If muon flux and hotspot shapes swing with the same clock that drives polarization and X-ray skin, we've caught a shared dial. One clean corridor case study makes this real. In the torus periphery sector, the TV excess tightens at a few TV, softens above 10, and its ridge traces the HI arc. On days when polarization angles drift clockwise toward a known set point, soft X-rays brighten by a few percent, then fade. FRBs skimming that rim show a modest DM shortfall in rotation that swings more than interior bursts. Stack a month of data and the correlations hold. It looks like a valve. What does a leak mean for contact? If corridors open on a clock, then outbound and inbound signals ride cleaner when the valve turns. Yell at the wrong time and you hear your echo. Whisper with the phase and a small beacon can reach farther than a megawatt tantrum. The wall isn't just blocking, it's selecting. We're not done proving it, but if a seam really behaves like a reflector and a valve, then the editor is visible. And once you can see the editor work, you can start to write around it. Natural versus designed. All right, gloves off. We've got 2 clean stories on the table. The natural story says a moving parade of massive stars blew up over the last 10 to 15 million years, carving overlapping cavities that merged into the local bubble. Turbulence sculpted the edges. Magnetic fields draped the walls. Cooling stacked skins. We're catching a living superbubble mid-decay, not a monument. The design story says the same ingredients are being held near set points. Shell thickness keeps clustering into narrow bands. Magnetic geometry stays coherent over long runs while a thin inner skin flips fast. Star formation on the rim lights up in pulses that look timed, not random. Same physics, different organizing principle, maintenance. So what really separates them? Not it looks tidy, we need odds. How many cross-modal coincidences do we tolerate before we change our prior? Start at the base. Independent datasets all say cavity with a shell. Gaia's 3D skeleton, dust tomography, HI arcs, soft X-ray glow, UV absorption, radio polarization. Good. Now the nudges. Dust ramps early along rim directions. Polarization vectors swing smoothly along the same arcs. Dispersion measures to very local pulsars sit on an electron floor and break slope near the rim. TV anisotropy rides a shell seam and shifts with energy. FRB's grazing active panels show small DM shortfalls and rotation swings that sometimes flip sign. Each nudge alone is fine. Together, aligned to geometry, they tighten. Fair counterpoints matter. Superbubble simulations reproduce sharp edges, filaments where shells collide, nested layers from repeated shocks, and long magnetic coherence without a builder. Live iron in deep-sea crusts at 1.7 to 3.2 and 6.5 to 8.7 million years ago screams nearby supernovae. Voyager 2's roughly 50,000 degree heliopause skin proves sharp plasma interfaces arise naturally. The Laniakea supercluster's roughly 600 kilometers per second drift toward the Great Attractor just reminds us frames leak. It doesn't demand a warden. The local interstellar cloud behaving like a Faraday filter is exactly what magnetized plasma should do. So here's the midpoint. Even if the bubble is natural, we still live behind a filter that edits light and charge. That alone means our rulers, candles, and particle baselines are curated by structure. The question is whether the interface merely relaxes or it is being held in an operating window. Let's score 3 design tells against natural expectations. Tell 1. Thickness and spacing. Column densities and ramp widths along multiple rim sectors bunch into narrow bands, tighter than a broad turbulent spread. That could be cooling physics picking a preferred thickness. But those same sectors also land at similar polarization twists, like field strength and geometry are co-tuned to that thickness. 2 dials lining up. Tell 2. Coherence with toggles. Background starlight polarization gives a slow backbone angle over years. On top of that, some panels show day-scale rotation swings during FRBs that snap back, while the backbone barely budges. That's a thin skin flipping around a set point, not random drift. Turbulence can swing, yes, but this looks reversible and stateful. Tell 3. Timing on the rim. Ages of young stellar objects around Taurus, Perseus, Ophiuchus line up like a wavefront marching the shell at near constant speed with more than one pulse. A single supernova can launch a ring. Repeats suggest recurrent drive or a standing mode. Feedback from the newborn clusters could sustain pressure, but the phase speed staying steady across varying densities hints at an adjusted push. Now the Bayesian move. Start with natural as the default because it explains the skeleton and honors the iron 60 clock. Update with each cross-modal alignment that lands on the same geometry and adds a reversible state. If the joint likelihood of all those hits under natural, unmaintained drops below natural, with maintenance, your posterior shifts. Maintenance here doesn't mean aliens with wrenches. It means gentle, ongoing energy input and boundary conditioning that keep thickness, temperature, and field strength inside narrow bands where filtering works best. Stakes escalate either way. If it's maintained, we're under protocol, biosecurity, signal hygiene, calibration, pick a motive, and contact is phase gated by someone else's settings. Push hard at the wrong time and you shout at foam. If it's entirely natural, the ethics fade, but the epistemic hit remains. Our local standards, extinction laws, dispersion priors, polarization baselines, bake in bias. Export them, export error. So what breaks the tie? A clock. If panels tick, if polarization setpoints, soft X-ray skin brightening, TV hotspot shape, and FRB rotation swings move together on a schedule, then the interface isn't just relaxing, it's being kept. And if that clock holds phase across seasons and cycles, we've crossed from pretty scar to operating mode. That's our pivot. We stop arguing pictures and chase timing. Build the phase chaser, map reflection gain off the rim, watch particle weather against panel states, and see if the dials move as one. If they do, we've got maintenance. If they don't, we tighten the natural model and deconvolve the sky anyway. Either way, the next scene is the same. Treat the wall like a device and see if it answers back. The edge is alive. If the wall is more than fossil rubble, it should show timing, energy, and feedback. The rim does. Start with the baby stars. Ages in Taurus, Perseus, and Ophiuchus don't scatter like buckshot, they ladder. Along arcs that trace the shell, the youngest groups line up just behind slightly older ones, as if a pressure front marched past and set clocks. Slide from Taurus east into Perseus and you see a few million-year step. Ophiuchus lags again. Not perfect clockwork, but the offsets fit a near constant wave speed sweeping the rim. Gas dynamics back it. In Co and HI velocity cubes, flows don't rush through, they slide along the shell. You see azimuthal streams, gas-hugging curvature, speeding through narrowings, easing through bulges. Stack velocity on density and you watch a compression wave squeeze, pass, and leave denser, cooler gas behind. Chart stellar ages against those flows and peaks follow the press. That's the cause and effect chain. Push, compress, collapse, stars. We can cross-check the pulse with layered tracers. Young stellar object classes give the near-term clock. Class I where collapse is live. Class III where disks fade. Pre-main sequence tracks add a few million years. Line them along the rim and pulses appear. Active, lull, active, separated by similar intervals in different sectors. A single supernova can launch one ring. Repeats hint at recurrent drive or a standing mode linked to the shell's geometry. What's doing the pushing? Adjacent superbubbles can crowd and thump. Newborn clusters on the rim add winds and radiation. Galactic shear stretches and stresses. But here's the odd part. The inferred pulse speed stays near constant across arcs with different densities. A wave crossing variable media should slow and speed. If it doesn't much, pressure might be adjusted. Gentle maintenance, not a single dying echo. Light catches the wall moving too. Remember the FRB corridor with the wrong sign rotation measure and that soft X-ray wink minutes later? That's a thin inner skin heating while magnetic geometry flips fast. UV absorption toward nearby hot stars shows ion ratios changing with time in some rim sightlines. OVI easing while CII and CII strengthen, consistent with a hot layer cooling after a nudge. Small swings, same story, a breathing interface. Polarization baselines split into two clocks. Starlight polarization angles along the rim drift slowly over years, a backbone field holding shape. On top of that, during certain transients, radio rotation can swing on minutes to hours scales and snap back, while the backbone barely budges. Two layers, two tempos. A stable scaffold and a quick skin that responds to pressure. That's how devices behave, structure plus a tunable face. Energy budgets have to close. A single core collapse supernova drops around 1051 ergs, but you don't get that every year. Spread over hundreds of light years and millions of years, the average push is modest. The pulses we infer are tighter. Winds and radiation from newborn rim clusters can supply steady pressure to hold the shell near an operating point, while occasional shocks or reconnection events retune the skin. Feedback closes a loop. Stars triggered by the wall help keep the wall in range. TV anisotropy patches add a live readout. In the Taurus periphery sector, the excess tightens at a few TV, softens above 10, and its ridge traces the HI arc. On days when polarization angles drift toward a known set point, what our phase chaser flags as open, soft X-rays brighten slightly, then fade. Ground muon counts tick up in step. Not every day, not everywhere, but often enough to look like a shared dial. Mirror efficiency. Electron column and field geometry move together. We can turn this into tests that don't beg the question. First, a rim cadence map. Continuous starlight polarization, pulsar and FRB rotation measures, and soft X-ray brightness along tagged panels. We're looking for phase. Do these three drift together? Second, a particle weather tie-in. Time bin TV hotspot morphology and ground muon counts by the panel's phase state. If anisotropy shape tightens when polarization angles hit the set point, that's the mirror breathing. Third, an in situ scout. Small probes on grazing arcs with magnetometers, UV soft X-ray spectrometers, and a chirped radio beacon. Measure the skin's temperature and field, then ping through at predicted reflector angles. Inside receivers watch for gain bumps and phase lags that stamp the panel's cue. Star formation timing adds one more lever. Ages around Taurus, Perseus, Ophiuchus point to at least 2 pulses, not 1. If we can pin the present phase, where the compression front is now, we can forecast which arc should light next. That's falsifiable. If the next burst of young stellar objects pops where the phase says it should, the wall isn't just relaxing, it's keeping time. We should also be honest about confounders. The heliosphere breathes on an 11-year solar cycle and can twist local polarization and cosmic rays. We handle that by comparing interior sightlines to rim grazes and by subtracting inner gate models built from in situ spacecraft. Turbulence can rotate angles and heat skins, but it loves random. We mitigate that by demanding geometry. Curves must ride known arcs, and flips must snap back to the same set points. Why does a living edge matter? Because if panels tick, corridors open and close on a schedule. Outbound signals ride cleaner in phase. Inbound transients distort less. Contact becomes a timing problem, not a power problem. And even if no one is listening, the science payoff is huge. A timed interface lets us deconvolve the sky with fewer free parameters because we're not guessing at static shells, we're measuring operating modes. So here's the pivot out of this scene. We stop treating the wall like scenery and start treating it like gear. We build the phase chaser. We map reflection off the rim. We fly a couple of cheap scouts and listen harder than we speak. If the edge is alive, it will tell us in clocks and corridors. And then the only question left is what those modes are for: biosecurity, signal hygiene, calibration, or all three. The architect's hypothesis. So if the edge is alive, we have to talk motive. 3 working functions make sense: biosecurity, signal hygiene, and calibration. They're not wild guesses. They fit the device behavior we've already measured: selective pass, reflect, and rotate with timing. Start with biosecurity. Life spreads on dust and ice like glitter. A pulsing rim that heats, compresses, then cools would scorch a lot of hitchhickers, slow cross-shell mixing, and force material to slide tangentially. That's containment. The 10 to 15 million year supernova chain gives you the skeleton, but the narrow shell thickness bands, the azimuthal flows, and those repeated star formation pulses look like ongoing conditioning that keeps transfer rates within bounds. You don't need intent to get function, but if anyone cared about spillover risk, this is exactly the kind of soft quarantine you debuild. Use physics that runs itself, then nudge it to stay inside safe ranges. Signal hygiene is colder but elegant. Galactic scale navigation and comms hate variable media. Magnetized plasma rotates polarization. Electrons disperse timing. Dust polarizes starlight. A layered interface you can hold near a set point becomes infrastructure. Keep Faraday rotation predictable. Hold the electron floor steady. Let corridors open on a clock so high priority traffic rides low noise. The FRB that showed a wrong sign rotation measure near a panel we already tagged as coherent, paired with a brief soft X-ray wink, is exactly what a retune looks like. Field geometry and electron content adjusted together. Function over motive, a phase shifter on a shared line. Calibration is the quiet one and honestly the most useful for us. Astronomy runs on standards. If you wanted a patch of space to benchmark instruments over eras, you want a hot, low-density cavity for low foreground, a stable, layered shell for repeatable polarization and dispersion, and a nearby shell perched population, fresh clusters on a schedule for distance and extinction checks. That's the local bubble. The rim's age ladder around Taurus, Perseus, Ophiuchus gives time-stamped yardsticks. The soft X-ray skin backlights nearby clouds so you can verify depths by shadow. The electron floor gives a known dispersion budget. You can calibrate a galaxy from here if the panel settings don't drift too far. Okay, but how would architects implement any of this without neon signs? You wouldn't pour metal plates in space. You'd co-opt natural cycles. Pick your scaffolds from what's already forming, overlapping superbubbles from moving groups. Then add or subtract pressure at the right moments so the merged shell keeps its thickness and field geometry in the sweet spot. Magnetic tension is your truss. Where you need reflectors, you compress and order the field. Where you need valves, you lean on saddles where fields thread out between adjacent cavities. Most of the work is timing. Small, periodic pushes that keep the interface in range, so the filter bank stays predictable. What evidence would we expect under architects that we can actually test? 4 tells we already sketched, now framed as predictions. 1. Shell thickness and column density bands should stay tighter than a broad, turbulent spread across widely separated arcs, even as local densities vary. 2. Magnetic geometry should hold a long coherence backbone while a thin inner skin flips fast and reversibly, minutes to hours, when pressure pulses pass, with soft X-ray micro-brightenings tied to those flips. 3. Star formation pulses should march around rim sectors at near constant phase speed, with more than one pulse visible in ages, not a single echo. 4. Dispersion and polarization tweaks along rim grazing lines should correlate with those X-ray flickers. Rotation up when the skin heats, down as it cools, while interior sightlines stay quieter. Counterarguments matter. Superbubble simulations can make nested shells, long coherence, and repeated compressions from natural feedback. Live iron in deep-sea crusts at 1.7 to 3.2 and 6.5 to 8.7 million years ago argues for real nearby supernovae, not stagecraft. Voyager 2's roughly 50,000 degree plasma skin at the heliopause proves sharp interfaces don't need a designer. The Laniakea supercluster's roughly 600 kilometers per second drift toward the Great Attractor is a frame leak, not a message. And the local interstellar cloud acting like a Faraday-like filter is standard plasma physics. So we separate skeleton from settings. Natural builds the room, maintenance holds the thermostat. Our job is to measure whether key variables sit in narrow operating windows longer than decay would allow, and whether flips are reversible and phase locked across bands. That's a device signature. Now the ethics people worry about. If this is quarantine, consent is missing. True, but function tells you how to behave. Biosecurity implies low-impact trials, no brute force beacons that could stress corridors. Signal hygiene implies phase-aware transmissions and full logs so you don't jam a shared line. Calibration implies we owe the catalog. Publish the deconvolved sky, the corridor map, and the phase schedule as we learn it. If someone is watching, that's protocol. If no one is, it's still better science. Here's the practical takeaway. We don't need to prove architects to use the room. We need to show that we understand the settings. Build the phase chaser to read panel state. Map reflection gain off the rim so we know the angles. Tie particle weather to corridor flags. Then, if we ever try a whisper outward, we do it in phase at a reflector angle, with power low and telemetry high, listening harder than we speak. Because whether this is biosecurity, signal hygiene, calibration, or just a very convenient scar, the interface is already doing work. If there are architects, reading the manual is how you get keys. If there aren't, the manual still makes the map truer and opens the door the smart way. The escape routes. All right, if the wall's a filter, not a fortress, we don't need to blow it up. We need to couple to what it already does. Think passbands, not battering rams. 4 routes make sense: reflections, valves, channels, and ghosts. Each one trades power for stealth, and each one teaches us the interface before we ever try a hello. First, shell reflections. The rim behaves like a weak mirror for some radio bands and particle pitch angles. So we map gain, not lore. Picture 2 small deep spacecraft with synchronized clocks and narrowband transmitters. They sweep frequencies while skimming interior lines that graze the rim at controlled angles. On Earth, a phased array listens off-axis for faint time-coded returns. If a panel has Q, if it rings, we'll see a gain bump and a phase lag where polarization twist peaks. That's pure calibration, no message, just a rim impulse response we can repeat. Bonus, those same sweeps give us a live transfer function to untwist starlight polarization in that sector. Second, polarization valves. Some saddle regions between bubbles thread magnetic field lines outward. Those look like topological gaps, easier exits when the thin inner skin flips to the open state. We won't guess, we'll watch. Build a phase chaser. Compact dishes tracking starlight polarization and real-time rotation measures along tagged panels. When angles drift toward the open set point, the one we flagged from FRB flips and soft X-ray micro-brightenings, we toss a micro-burst, millisecond low power at the corridor's plasma-friendly band. If the burst lands back with less twist and delay than baseline, valve confirmed. If the skin answers with a spike in rotation or X-ray, we back off. We're learning the timing, not kicking doors. Third, ride the particle channels. TV anisotropy already points along bright seams. We can tag that river without dumping power into space. Release a tiny metered puff of noble gas, neon or argon, from a CubeSat station where the seam crosses inside lines. Passing primaries will spall and goose a faint, predictable secondary signature. We modulate release times in a prime sequence. Arrays on Earth watching that patch see a spectral wink that rides the seam's energy curve. That's not a chat, it's a marker. Someone inside understands transport. If it spooks you, good. We treat it as last in line, only after year-long monitoring says the seam is stable. Fourth, ghosts, neutrinos. The wall won't care about them and they won't jam anyone's corridor. Power is the pain, so we use breadcrumbs, not broadcasts. Upgrade an existing accelerator's timing discipline. Gate pulses with lunar occultations for a clean on-off edge at distant detectors and send a tiny codebook, counting primes, hydrogen line, our corridor map indices. If no one's listening, we burned a little electricity. If someone is, they'll see we value hygiene over hype. We won't roll these blind. We run a 3-axis score for each route, medium disturbance detectability by third parties and scientific value even if no one answers. Reflections, low disturbance, medium detectability, high value, because the same experiment feeds our deconvolver. Valves, low to medium disturbance depending on phase accuracy, medium detectability, very high value, operating modes in hand. Channels, medium disturbance locally, high detectability in that lane, medium value, great control proof, modest science. Neutrinos, near zero disturbance, low detectability except by the advanced and high protocol value. So what's the order of play? Reflections first, as pure mapping. We fly the twin sweepers on slow arcs through 2 rim sectors, torus periphery and an opposite, quieter panel. We tie their sweeps to the phase chaser clocks on the ground. If returns show angle lock gain and stable phase lags, we publish the panel Q and the untwist kernel. In parallel, we stand up the phase chaser network. Small dishes, magnetometers and soft X-ray monitors watching tagged panels continuously. We push live, open-closed flags to observatories so anyone can mark data by corridor state. If nothing else, that kills hours of arguing over weird residuals. 6 months in, if the phase schedule holds, we trial a single-bit valve test. 1 millisecond chirp during an open tick at a reflector angle, power low enough to hide under galactic noise at distance. We're not trying to be heard, we're trying to watch the wall ignore us. If the skin twitches, rotation spikes, soft X-rays wink, we pause and rethink. If the corridor stays calm and our deep arrays see the predicted untwisted, low delay echo, we've locked a passband. Particle tags wait a year. If TV hotspots and ground muons track panel phase without surprises, we schedule 2 micro puffs, months apart with full environmental logging. If the seam reads it clean and nothing downstream flares, we notch confidence. 1 strike, unexpected heating, rotation chaos, and we retire the play. Neutrino breadcrumbs run regardless, at academic cadence, with public timing and content. It's our we can be quiet calling card. You'll notice a pattern. Every move measures first, whispers second, and leaves logs others can check. If there's a warden, that's good manners. If there isn't, it's still good science. Because the real escape here isn't out of the bubble, it's out of our own bias. Learn the settings, ride the phase, use the wall as a tool. Then, if we ever do step through a scene, we'll do it like adults, on purpose, on schedule, and with the room's consent. Breaking the filter without breaking ourselves. Here's the move. Stop arguing the wall is a filter and start undoing the filter cleanly with receipts. We build a sky deconvolver that's open, modular, and testable. No black boxes. 4 layers, 1 cause and effect chain. Layer 1, polarization. We untwist the shell's Faraday rotation with a live rotation measure grid. That grid isn't theory. It's built from pulsars, FRBs that skim the rim, and our own reflection pings grazing the wall at mapped angles. Subtract that rotation, and we get intrinsic polarization angles for background sources instead of angles draped by the interface. Layer 2, extinction. Dust is weirdly thin inside the cavity and piles in bands at the rim. Tomography undercounts that foreground in some corridors. So we add back extinction using the shell's column density bands tied to Gaia distances and UV absorption of CII, and OI that pushes nearby clusters dimmer and redder by a hair, where they should be. Layer 3, dispersion. The cavity sets an electron floor. We pin it with very local pulsars and FRPs that graze the rim, then weight dispersion so radio sources sit at distances that don't pretend the floor is zero. That stretches a few lines of sight without touching geometry. Layer 4, soft X-ray backlight. The hot inner skin brightens and casts shadows against nearby clouds like Taurus and Ophiuchus. We measure that backlight with soft X-ray monitors and remove it with a transfer function that depends on panel state from the phase chaser. That flattens false glow and gives a truer faint background. Now we stress test the pipeline with messengers the wall can't edit much. First, gravitational lensing. Light bends by mass, not by electrons. If our deconvolver is honest, mass-to-light ratios for nearby groups shift toward values seen outside the cavity because we've stopped making locals look too clean and close. Second, standard sirens. When neutron stars merge, gravitational waves set distance without caring about dust or plasma. Compare that to deconvolved M distances along the same sightlines. If they match better than raw, the fix is real. Parallel to that, we touch the wall, gently. We launch 2 tiny rim-grazing scouts. Each carries a triad, a magnetometer to read field angle and strength, a UV soft X-ray spectrometer for the thin hot skin, and a micro-transmitter to chirp across radio bands at mapped reflector angles. The probes measure the layer cake in situ, then ping back through it while our arrays on Earth listen off-axis. If returns show the predicted gain bump and phase lag, where starlight polarization peaks, we've nailed the panel's impulse response. Back home, we publish double vision by default. Every nearby object gets 2 entries, filtered and reconstructed. Distances, Gaia raw and deconvolved after electron floor and dust fixes. Polarization, as measured and untwisted by removing shell rotation. X-ray brightness, raw and cleaned of inner skin backlight. We tag each sightline by panel state, open, closed, ambiguous, so anyone can pick a source and see what the wall did that day. We keep ourselves honest with nulls. Rotate polarization where the rim isn't. Residuals should go to noise. Add dust where reddening is already high. The fit should worsen. Change the electron floor in directions far from the cavity. Dispersion should break. If corrections help rim tide sectors but hurt the quiet sky, we know we're targeting the right layer. Then we swing for the gut check. Rebuild cluster ages and radii with the deconvolved distances and extinctions. Hertzsprung, Russell diagrams tight. Some overluminous members drop in line. Exoplanet radii sag by a few percent where host stars were too bright. Not sexy, but huge. After that, lay the corrected star maps against background lensing shear. If structure behind the rim correlates more cleanly with the mass map post-deconvolution, the local smear was real. We point the deconvolver up a scale to the Milky Way itself. Spiral arm contrast, bar length, warp amplitude. These were inferred with local baselines. If the shell-made neighbors look cleaner and closer, arm contrast softens and the bar might stretch after correction. That's a hard pill, but better a true map than a curated one. Now guardrails, we do not blast the rim. Science first, scout second, micro bursts last. If the shell twitches, soft X-rays flicker, rotation snaps, we stop and remodel. The point isn't to shout, it's to learn the room. We also change habits. Observatories run phase-aware cadences by default. Polarization and rotation measure feeds sit on the same dashboard as weather. TV arrays and ground muon stations time bin by panel state. FRB catalogs add a rim geometry crossed field next to DM and RM. Lensing teams flag mass to light outliers by corridor state before they fight about feedback. Here, why this wins even if no one's guarding any switch. A phase-aware sky is a cleaner sky. We stop pretending our yard is neutral. We make two catalogs for everything. What we saw through the filter and what it likely looked like without the filter. And we stop burning money on brute force beacons. If corridors open on a clock, timing beats power. By the end of this, either the wall is just physics and we've finally modeled it, or it's physics with settings and we've read them. Both are wins. One hands us a truer galaxy. The other hands us etiquette for a shared line. Either way, we break the filter the smart way, on paper first. Then only if the room stays calm with a whisper. If the dead zone is real. So let's say the filter is real and we treat it like gear, not scenery. Day one, we add a local interface column to every catalog. Distances get two numbers, Gaia raw and deconvolved after we add back the cavity's electron floor and the rim's thin, patchy dust. That nudges some nearby cluster distances by a few percent. Small on paper, big in practice. Stellar luminosities shift, so exoplanet radii that leaned on those stars shrink a bit. A few super-Earths slide toward mini-Neptune. Habitable zones inch inward, because the hosts aren't quite as bright as the curated sky made them look. Backgrounds get easier to trust. We stop treating soft X-rays like a flat haze. The hot inner skin backlights nearby clouds. We measure that glow and subtract it. Galaxy clusters behind the rim pop cleaner, and the shadows they cast against the backlight become calibration tools. That lets lensing teams tighten mass maps, because the false local glow is off the table. When mass-to-light ratios line up better after the deconvolver, we know the fix is doing real work. Cosmic rays get a two-track life. Spectra are reported as measured and desieved, with the cavity's transport put back in. Dark matter hunters and pulsar modelers can flip between views. Ground muon networks add a new field alongside solar data, panel state. If a rim sector is open, they tag counts accordingly. TV arrays time bin anisotropy maps by the same flags. The point isn't drama, it's phase awareness like weather. We stop arguing over weird residuals because we can now say, that spike rode an open corridor. Voyager's heliopause profiles get a new frame. The roughly 50,000 degree skin becomes the inner gate of a two-gate system. That helps space weather folks because the outer gate, the warm local interstellar cloud and the rim's ordered fields, sets long baselines that modulate what the heliosphere can even work with. Radiation forecasts for interplanetary flight fold in the panel state. Quiet days get quieter. Pinch days get warnings. The rim's age ladder moves from trivia to metrology. Taurus, Perseus, Ophiuchus sequences become timestamps to cross-check the phase chaser. If a compression pulse should reach a given arc next season, surveys schedule deeper looks now. When young stellar objects spike on cue, we bank the phase, update the corridor map, and publish. SETI pivots hard from brute force to protocol. Fewer megawatt beacons, more timing. We put reflection mapping and phase chasing in the open. Anyone can see when a panel drifts toward open. If someone else shares the corridor, they'll also see us prefer low impact. Millisecond test chirps at reflector angles, power tucked under galactic noise, full telemetry. Neutrino breadcrumbs run on a quiet academic cadence, rare, precise, public. It's a signal about signals. We know hygiene matters. Policy follows. Phase windows become public goods. Observatories and arrays post open-closed flags like cloud cover. Quiet hours get community support during sensitive states. If the wall heats and twists, soft X-rays flicker, rotation spikes. We pause outbound trials and treat it like a fire risk because it might be. Education shifts to systems, not snapshots. Kids learn why a magnetized plasma can behave like a device without a designer, and how function still gives you handles. Labs build benchtop analogs, layered plasmas, aligned grains, and watch polarization and dispersion flip at thresholds. Engineers get jobs out of it. Phase-aware comms, corridor-safe protocols, transfer function deconvolution. Those aren't buzzwords, they're tools. We also get honest about maps. The Milky Way's spiral contrast, bar length, and warp amplitude all leaned on local baselines. After deconvolution, arm contrasts soften a bit. Some bar measurements stretch. That stings pride, not physics. Better a true map. Gravitational lensing and standard sirens referee because they don't care about electrons or dust. If the deconvolved distances match siren distances more often, the room was warping our rulers. Psychology adjusts. Living under a ceiling you can't touch but can time is weird. Some people will go doom, others will claim angel glass. The middle path is steadier. We admit we were looking through a filter. We build double vision by default. And we treat the rim as shared infrastructure we don't own. Final practical bit. We pace ourselves. Science first. Phase Chaser online, reflection maps built, Deconvolver open sourced with null tests. Scout second, 2 tiny rim grazers, 1 quiet panel, 1 active. Micro bursts last and only in phase at mapped reflector angles with watchdogs on soft X-rays and rotation. If the room twitches, we stop. If it stays calm and the returns match the model, we keep going, lightly. Do this right and 2 things happen fast. Our sky gets truer, and our manners get better. If there's a warden, that matters. If there isn't, it still does. Because the point of a lock isn't to scare you, it's to make you learn key. By the time you see the filter's fingerprints, you can't unsee them. The sky stops being a backdrop and starts acting like gear, with settings you can read and sometimes use. Subscribe if you want to watch us ping the rim, publish the first phase-aware deconvolved sky, and fly the scouts. Share this with someone who thinks void means empty. And drop your best low-impact test idea in the comments. Tools only, no hero beacons. If we're quarantined, fine. We'll turn the cage into a lab and earn the key.